So this week we'll finish all the N-Well resistor stuff and cover C5 layers, which is the integrated circuit chip. All the layers, including the oxide and the metal layers, diffusion, all these kind of things for layout purposes. Very important topics. And operation of MOSFETs, NMOS, PMOS, how to form logic gates using MOSFETs. And there will be a quiz on Wednesday about C5 layers. Basically just drawing. I'm going to cover this topic today. So see what's really going on. And MOSFETs operations will be a really short quiz. Very simple. Just draw IV curves of MOSFETs. Two quizzes this week, and one homework assignment due Friday. And definitely one lab on Thursday. Okay? So someone had a question regarding the sheet resistance for the N-Well resistor. I think we have a lab on Thursday regarding the N-Well resistor layouts. So the question was, why a smaller square has the same resistance as a bigger square? Right? So the resistance equals rho. Let's draw it first. Here's the rod. Here's the rod. N-Well. Okay. What's the dimension here? Remember? T. That's the thickness. If you look from the side, this is a silicon wafer, even though it's really thin, but if you can still look at it under the microscope. So the N-Well is just a well. It's an N-type material. Right? So if you look from the top, one more time, this is side view. If you're from the top, it could be just a rectangle like this, just a box. Okay, look from the top. So that's also N-Well. This is top view. If you extract this feature or this kind of material, extract it from the wafer, it looks like a rod like this. Okay, so this is the thickness, which is here, this dimension, thickness. And you cannot change it because this is defined by the foundry's fabrication process. It's not changeable. And you got this one is the length, and this is the width, right? So the resistance of this layout from the top, since when you are laying out this in electrical VLSI, you are laying out the top view, right? So the resistance of this layout equals what? Equals I just want to give you more information to make sure I'm not making a mistake over here. That's rho, which is the resistivity, times L over thickness times the width. Okay, and this one equals rho over T, multiplied by L over W. And the sheet resistance specifies this parameter because none of them are changing. So the resistivity of the material is depending on the property of the material, so it's not changing. And the thickness is defined by the foundry, it's not changing. So this is a constant. And this is called the sheet resistance. Remember the example we have? I told you the sheet resistance of the C5 technology, the 500 nanometer technology, is like 800 ohms per square. It's somewhere around that. So in that case, if this is not changing, and the resistance depends on the ratio of the length and width, right? So in that case, if you have the same ratio, the resistance is not changing. And that is why a smaller square and the bigger squares have the same resistance, because they have the same L to W ratio, right? Does that make sense? So when you are laying out a resistor, you want to pick up the minimum W, So you can use the minimum dimension extended in the dimension of the length to form a certain value of the resistor, okay, or the same value of the resistor. So you don't have to, if you double your width, you need to double your length as well to realize the same resistance, which is taking a lot of area in the die. Okay, so you have limited area on the die, which is the wafer, the chip, die. Okay, so you want to reduce the footprint of every single component as much as possible to save money. Any question on this? No. And now let's talk about C5 layers. It's not a secret. Doesn't like the 180 nanometer technology from TSMC, even though it's a 20-year-old technology. We can still not disclose the number of metal layers to you guys. So you guys have to sign the NDA, and eventually everybody knows it, but we cannot just talk about it in the class. Or I can record it, but I cannot publish to YouTube. But C5 is simple. It's 40-year-old, so it's easier. C5 layers. So there are 3 metal layers. It's not a secret anymore. Okay, 3 metal layers. So how that works? So starting from the wafer. Usually it's a P-type substrate, P-sub. So what's the first layer? So most of the time it's called a Fox, but let's draw the little diffusion here as well. So Fox. It's not flat, that's why I have to draw it this way. N plus, you got another Fox. P plus diffusion, another Fox. Yeah, I think I'll just draw 2. I'll just do this. Fox means filled oxide is trying to avoid crosstalk between this diffusion, because eventually this will be the drain, the source, and all these terminals of the transistors. They are running currents in the channel through the terminals. So the Fox will be little plugs in the middle to reduce crosstalk in between these diffusion nodes. And there will be another layer right above it. Okay, even though it doesn't make sense to have a polysilicon layer over here, but you can do it. It's not, probably nobody's doing this, but just show you, you can fabricate or lay out a layer or a feature in this layer. So this is bottom, okay? So using a bottom up manufacturing process. So this is a polysilicon. It's used to form gates. It's a gates of the MOSFETs, Or can use polysilicon material to form capacitors. I think we'll be able to have a chance to lay out the capacitor using 2 layers of polysilicons. So I'm drawing 1 poly here, but actually you just need to know there are 2 layers of poly. Poly 1, poly 2. This is poly 1, for example. And there'll be another layer at a different depth here. It's called poly 2. It's really interesting. I'm going to draw the figures later, but you know how to draw a capacitor in your layout. So you got a poly 1 here, okay, and you have a poly 2 as well. And here's your metal. You draw a metal wire, another metal wire. So this overlapping area forms a cap. That's usually how we design the capacitor in the chip. Okay, that's how that works. What's that?
Is that air in between them, or?
Yeah, the area between them,
okay.
The overlapping area between them. So this part is not being used. because there's no overlap. The reason we have to get all the wires going up is because all the chips, they have all these intermediate layers of metal, and there won't be any access to the middle layers. Eventually, you have to build all these layers, and eventually on the very top of the chip, you have a little opening, and you can use a wire bonder to bond it to the top metal pads, and eventually, either inject signals into the chip or probe it from all these pads. Let's keep going, right? So above that will be another layer. So this material is a physical material being deposited onto the chip. This is called the insulator. But usually this is silicon dioxide. Same to this one. So they have to use all these silicon dioxide as an insulator in between layers. Otherwise it will be short circuits. So how do we make the connection in between the layers? You drill a hole. It's called a via. These are tiny holes. It's called via. Vias. And then this is insulator for this whole layer, but you can have metal layers inside the insulator. And so this metal one layer has a direct contact with the via, so it's able to make the contact or directly short it to this P+. So we'll talk about what P+ is later, but now you just need to know that the P+ is a P-type heavily doped or highly concentrated P-type material as one of the terminals of the transistor, which we'll talk about in a bit. Okay, so P+ is a material, and you can drill a hole through this insulator and directly make the contact with the metal one layer on the top. And you have another metal layer here. Again, drill a hole, no problem. And that's metal 2. Okay, this is metal 2. All right, here's our final layer of metal. And of course, it's called metal 3. It's metal 3. So the material used to insulate the layers between the metals is always silicon dioxide. It's an insulator in between them. Okay, so you can tell that if this is a silicon chip, we don't have any access to any of the signal lines yet. So the way to do that is, just in case, okay, so gate. Here's a polysilicon, which is a gate of the NMOS transistor, for example. So NMOS transistor, you got drain, source, and gate. All these are metal ports. Okay, so we'll talk about the details of this operation later. Don't worry about that. So this is just a transistor has 3 terminals, and the terminals need metal wires to either inject a signal into it or being probed by something. Okay, so these are metal. Okay, so this material over here for the gate is a polysilicon. It's not metal, but the thing is, we do need a metal to give a signal to it. So you need a via, okay, and you need a metal one. Okay, if we don't want anything else, we just directly want some signal being connected to the outside world. Okay, so we just directly drill the hole up. Keep going. It's metal 2. Drill the hole. And metal 3. And there's a layer. There's a layer of fabrication process. All these layers are being fabricated by something called masks. I think the semiconductor class I think that's ENGR 430, I believe, by Dr. Jessin will cover the details about how the masks works for the photolithography process. But anyway, so all these masks will be able to define the layer on the top of the metal, and we'll have an opening on the top. So this top silicon dioxide can be opened up by a chemical, right? So it's gonna open up on the top and eventually expose this metal 3. So metal strip exposed. And they can use the wire bonder. It's a $20,000 machine in my lab, okay? And it's functioning, which is important. So a lot of wire bonders, like for example, the one we had like 3 in my graduate school, and none of them work. So we have one which is functioning, and so we can wire bond it to all these openings on the metal strip layer. Okay, it's like a wire bond. I can show you really quick. Let me introduce every single one to you guys. I'm kidding. It's gonna take like a few hours. So these are metal strip openings. So this is it's called a pad. Show you. Bonding pad. Bonding pads. So these are bonding pads. I think the one I showed you was 75 micrometers squares. Okay, has a little hole in the middle. And that's a bonding wire. Okay, it's really thin. You can see if this is 75 micron, and the wire's diameter is probably like 20 micron-ish, and they're gold because they're really thin. So it's going to introduce a lot of resistance. As gold has a better conductivity. So these are the pins of the chip, and that's a little cover. And I showed you guys on the first day, so there's a little silicon die in the middle, which is a chip. So this chip's dimension is about 1.5 millimeter by 1.5 millimeter. And these bonding wires are bonded to smaller pads in the middle of this, underneath this cover. So there are smaller pads, so you do the wire bonding inside this area, and these pads inside, you cannot see it because it's getting covered by this little lid. So these pads are connected internally inside this ceramic material, which is a package of the chip. And so all these pads inside are shorted to every single pin, the 40 dip pins of this chip. So there are 40 dip pins, starting from the little dot here, which is pin 1 usually. So if you pay attention to this one, it has a little notch on the top, and that indicates the orientation, which is the top. And so the one on the left hand side is usually pin number 1. And the way to count the pins is from here to here will be pin 1 to pin 20, and then directly move to the right will be pin 21. And so this pin here will be what? Pin what? 40, right? So the 40 dip package. So the name of this package will be, you'll see this a lot in the future because this is very standard, probably the lowest cost package you can get from the market. And we're using this kind of package for our chips in the future. So it's called a dip dash 40. If you'll see this, you'll know it's the package I just showed you on my website. All right, any question on this? Good so far? Okay, let's move to all the drawings. If I show you a layout like this, I'll let you draw on your paper first, okay? This is the layout, and I'm telling you that this is the via. So the vias have numbers as well. So for example, this you can name it whatever, but I believe this is via 1. Let's call it via 1, all right? Doesn't matter. And this is metal 1, and this is metal 2. Can you draw the cross-sectional view of the chip for me? I just do this, okay? So for example, this is P sub. P sub. The substrate, the wafer itself. Do we have any diffusion here? Do we have any diffusion like P plus N plus in here? No. The answer is no. Just 2 metal wires doing some fancy stuff. So no diffusion, which means the Fox layer will be interconnected. So there's nothing to open up the Fox. So the Fox is a homogeneous layer being deposited on the top of this P-sub. So there will be one homogeneous Fox layer on the top, so which means we need to draw that first. I know it's not flat. It's weird to look like this, but that's how we do it. It goes into the wafer a little bit, you know. Sarah is like, how do we do that? High temperature, high pressure in a vacuum, probably. So what's next? So immediately above it will be what? An insulator. Insulator to host which layer? This insulator is for which layer? For which layer? Did you cover this in semiconductors a little bit? A little bit? Okay, cool. Yeah?
I don't think we've gotten there for like class-wise, but research, so it's just.
Not yet? What is in here? You know the answer, right? Do you? I saw too, yeah, but inside, what's in there? What's this layer for? The poly, right? The poly, the gates. The gates. So, do we have a gate material over here or no? Do you have a gate material? No, it's just two metals. So now let's keep going up. There's another silicon dioxide. There's also silicon dioxide. The insulator, right? For poly is for what? Metal 1. So we do have a metal 1 here. So how do we draw it? Okay, so here's a cross section. Should have specified that earlier. If I don't specify that, you can just draw nothing in there because you can argue that, hey, I'm drawing a cross section here. You'll still get 100. That's my fault. So if I draw a line here, what are you going to see from the side? That should be accurate. That's the length of it. Definitely over here we got a metal 1. It cuts through this little via, so we got a via. Via is from metal 1 to the bottom of the metal 2 layer. Because that's the goal of it, right? That's everything about it. It's trying to make a contact between metal 1 and metal 2. And then metal 2, we got another silicon dioxide. Okay? So there will be a metal 3 layer, but there's nothing in that layer. So just draw it, draw that silicon dioxide, and label it. Okay, there will be a quiz similar to this one, but there will be probably more different layers on Wednesday. But I think you know how to do it, right? Something similar to this. So it's really simple because there are only 3 metal layers. You don't need a lot of space on the paper to draw all these different number of layers. The TSMC 180 nanometer technology, which we are going to use towards the second half of the semester, has more layers of metals, which I cannot disclose, but you'll find out. So more layers will be more helpful to have a more highly integrated circuits because you are able to route your wires in a relatively more concentrated area. Okay, because whenever you see you cannot route it through all these wires, you can always dig a hole and route it on the top, right? So more metal layers will be more helpful for layout. Let's see another example here. See if that's making sense. Oh, there's something about design rules. We don't need to memorize any of the rules because eventually, even for electric vehicles as a free software, it has the lambda lambda rule embedded inside the software. So eventually when you are placing the metal, like metal 1 and metal 1, you are placing them too close to each other, and there will be an error showing in the view, in the window. So you can tell they are too close to each other. So eventually you don't need to memorize any of the rules, but you need to know that there are certain design rules to define the minimum space between metal 1, or the space between metal 1 and metal 2, and the space between metal 1 and vias, things like that. So for example, the metal 1 to metal 1 minimum space is 1.5. It just tells you it's 1.5, but what does that mean? It's 1.5 lambda. Keep in mind, all the numbers doesn't have a unit with it. In this lambda rule design process, the unit will be lambda. So 1.5 means 1.5 lambda. So lambda in here is 300 nanometers. So 1.5 means 450 nanometers. So that's the minimum distance between metal 1 traces. Okay? If you place them closer than that, there will be an error indicated in the window. You can see it. You can tell. And similarly, it could be metal 2 as well. Okay? So metal 1, metal 2.
You cut out. You cut out.
What did I do here? Technology issues.
Maybe they didn't follow the lambda rule.
It's flashing. Oh. Okay, cool. Yeah, in the past when I was younger, I was anxious about everything. Whenever something happened, I got super nervous. Oh, how should I solve that problem? Get anxiety. Now I just learned, just allow everything to happen. That's all right. It happens and it happens. The same to metal 2, okay? Metal 2. I think they have the same design rules. M1 has the same, the 1.5, metal 2 has 1.5 as well. And we don't have to cover other rules since I couldn't memorize them as well. So that's just a pass to the second topic over here, which is backup vias, which is important. You'll see this kind of layout a lot when you are just directly making a connection in layout. They'll directly generate an array of vias. You probably will be wondering why. So let's take a look at this. M2, M1, a little via, definitely you need a via, otherwise there will be just two parallel metals in two different space. So sometimes if you have a thicker metal, if you have a very thin or narrow metal trace, it probably is only generating one via. But if you have a pretty wide one, for example like this, a wider one, so you have more space for more vias. And eventually, electric VLSI will directly generate an array of vias in here instead of just the one. And I want to let you guys think about this. Why they want to do that? Why do they have to do that with the wider wires? So for this one, they are not able to because they have limit space in between the two metals, right? So they don't have space for more vias. But now when they have more space for more vias, they would just directly put an array of the same vias inside, try to make the connection. So you can imagine it's basically two metal layers in two different space, right? Have two poles making the connections. So there are three benefits of doing this. Okay? So one, it is able to lower the resistance. Why? Because every single via has a resistance. If this is metal 2, this is metal 1, right? So the via has a resistance. So you got 4 in parallel. so it can reduce the resistance, which is important because a lot of times in the nanoscale there will be a lot of really thin wires routed for a long distance, so it's going to introduce a lot of resistance. The chip doesn't have a big area, but the thing is the wires are super thin, so that's why the resistance will be pretty significant. So it's introducing time delays. So for the digital chips, we have learned the RC circuit, so we know that if you have a different resistance, it's going to cause a different time delay, right? If we're trying to deliver the same clock to two different circuit blocks, but eventually they receive it at a different time, there will be issues. So time delay could be very important thing to consider. And a lot of times when you are doing a PCB design, a lot of times we ignore that resistance issue as well. But just let you guys know, when we are doing a PCB, the traces in resistance is also very significant. So for the default, I think that was 0.6. I forgot the dimension exactly, but for the default dimension for the traces in Eagle PCB, if you directly use it to route everything, and you can find out there will be like somewhere around like 0.3 volts getting lifted from ground. You got a ground here, which is 0 volts, and over here, same ground, but it's getting like 0.3, 0.4 volts. Because of the resistance, it's causing a voltage drop. It's very significant. So you want to make wider traces of the wiring when you are doing the PCB design. If you have a lot of traces on PCB. So it's a very similar concept over here. The trace resistance is really a big deal. So this is the first benefit, to have several backup vias in between metal 1 and metal 2. Okay, this wire is annoying. Sorry. I ordered a extension cord for the HDMI, so it will be better, I think, from Wednesday this week. I know this issue here. So number 2 is it lowers the current for each via. Why? Because these are same resistors, and if you have several resistors in parallel, they are forming a current divider, right? Number 3, get some backup vias. So there's a certain percentage of the yield for the chip fabrication. A lot of times you got a big wafer, so it slices it into different areas as a wafer, 75 inches or something. So we got, for example, only this area of all the chips are functioning, but all the ones on the edges probably will have some issues. Okay. But fortunately for 180 nanometer technology, TSMC, 180 nanometer technology, what I heard, their yield can reach up to like 98%. So which means we got a big wafer, and 98% of the dies are functioning. That's crazy, and that is why TSMC is just getting so popular. It's taking almost 90% of the market share to fabricate all the chips for Samsung, iPhone, and everyone. Its yield is so high. So for example, Samsung is able to make 180 nanometer technology for example 95% yield. Same technology, but 95% at the same cost. And eventually Samsung will get none of these contracts. So only the first place, only the first one will win the whole market. That's just the feature of this semiconductor industry. Okay. active layers and poly layers. So active layer opens up the flux. So which means you used to have a homogeneous layer of the flux deposited on the top of the P sub, and this active layer is going to open up a window on the top. So you must be wondering what is really happening over here. What is happening? Why an active layer is going to open it up? It depends on all the fabrication process, okay? So what's really happening is, for example, this is the wafer. This is the wafer. I'll just show you a really simple fabrication process, okay? It's a wafer. And first you spin a, let's say you have this flux layer here already, okay? Flux. Flux is probably using a different fabrication process. Okay, so let's say this is the metal layer, metal one. It's not a CMOS technology anymore, okay? It's not a CMOS. I'm just showing you a basic photolithography process over here, okay? So for example, I deposit a metal one on the top of the wafer, okay? And then I have a mask as a feature of the opening over here. So these are just the ink of the mask. It could be chrome, could be anything else, but it's type of ink. It's not really ink, but could be chrome, could be something else. It's just dark. It's just dark. I put it on the top. Okay. Then I'm going to expose the whole thing under UV light. So UV is going to get through here. But before that, I need a photoresist here as well. Okay, photoresist. Another layer. It's being coated. It's called photoresist. It's a photosensitive material. Okay, it's being coated on the top of the metal one, and you put a mask on the top. So this mask is your design. So this hole could be a wire, could be anything, or opening on the mask. So exposed under UV, the UV is going to cure this little area because it's able to get through and cure this area. So it's going to change the property of this area. If you remove it, remove the mask, and you are getting something like this. Remove the mask. There will be one. Still the metal one, right? Still the metal one. Metal one is still here. It's not changing. But the photoresist has changed a little bit because this part, it's a cross link, but this part becomes a little bit different texture compared to the rest. Okay? And then the next step, so keep in mind, this is called a mask. Okay, this is called a mask. It could be one of the layers you drew in the electro VLSI. So all these layout wires and traces in electro VLSI, these are, so you guys are actually drawing the masks for the integrated circuits. Keep in mind. So all these kind of things, the metal one traces, they are masks. Okay, eventually they will be printed on different layers of masks. So for example, this is one of the masks you are applying, trying to define the metal ones layer. Okay, so apply this one, expose it to under the UV, and this one get cross-linked, or the texture got changed. Okay, so this is photosensitive material. The texture over here got changed. And then the next step will be developing, right? To develop this. So just place the whole thing in a beaker. Okay, in the beaker. And this material is an organic solvent. It's called developer. So what this is going to do is, depending on the photoresist types, okay, so this is, for example, this is a negative photoresist. So eventually, the developer is going to dissolve all the rest part of the photoresist, so all these will be gone. And after the developer process, you are having this left. Still metal 1, okay? But you only have a little photoresist. This one got exposed to the UV left on the top of the metal 1. Okay? So next step is you place this wafer into an etchant. We'll remove the metal 1 because this part is protected by this little photoresist. It's being protected, it's being covered, so it's not going to be exposed to the etchant. But the rest of the metal 1 will be exposed to the etchant. Eventually they will be gone. So after this process, after this step, you're having this left on the wafer. So this is the photoresist, and this is metal 1. This is metal 1. This is the photoresist. Okay? And then you place the whole thing into another chemical. It's going to strip off this photoresist on the top and eventually give you this. Metal 1 left in the wafer. Okay, what is the goal of this entire procedure here? You can imagine this could be a little metal dot or could be a metal trace. So in that case, eventually you fabricated a metal wire on the wafer by using this mask. Okay, by using this mask. So this is just a very simple example. You can imagine you have a large-scale circuit. All these layers will be printed into masks and eventually being fabricated on the wafer in different layers. Okay, they fabricate a layer and deposit a silicon dioxide for that layer to insulate it, and then go up, fabricate another metal layer, and deposit another silicon dioxide on the top to insulate it. Just keeps going up. So it's called bottom-up manufacture procedure here. Eventually can get all the layers done. So you guys are doing the layout, it's basically doing the masks. Just keep that in mind. So the layout doesn't have any electrical properties. They're not even circuits. Because the masks are not even circuits. You drew the schematic in either electric VLSI or LT-SPICE. So these are electrical circuits, right? So, or netlifts to make all the connections. But for the electrical VLSI, when you are doing the layout, they are just joints, just masks. Okay, these are not circuits. Keep that in mind. So I can use electrical VLSI to draw a feature and eventually print it out as a mask and to fabricate something else. I used, it's called microfluidic devices. I just used all these masks to fabricate a photoresist feature on the top of the wafer to make microfluidic channels for biological purposes, all these kind of things. So, which means, you know, electric VLSI just a CAD, right? Just a CAD. It's a drawing tool. It's not a circuit simulation tool. All right. So eventually, you can reach here for a metal traces or features. So let's come back for this active layer. Okay. So this one, when I'm talking about active layer, will open up the Fox layer. Okay. How that works. So if I'm drawing a little square on the top, which means this is basically a mask. So the active layer in your electrical VLSI layout is basically just some kind of drawings. It will be part of the mask. Eventually, we'll be able to open up this certain area. So there will be, certain kind of ways will be different from these ones, but will be similar, right? So you apply a photoresist, cover something, and then expose UVs, and eventually using some agent, some chemicals to remove this part of the on the top of the wafer. So the active layer will be able to, is a mask, part of the mask will be able to open up the FOX layer. So after this is being opened, so FOX, so P sub, after this is opened up, you can apply the dopant in the vacuum, high pressure, high temperature, or what kind of conditions you need in the chamber. So the N-type or P-type materials will be able to diffuse into this substrate. So eventually you are forming a P plus or N plus, depending on your applications. If you apply, if you use an N plus material, eventually you are forming a N-Well. Okay, so if you form an N-Well, you can use N-Well for all different kind of purposes. Can be a resistor, can be an N-Well, you can put PMOSes into the N-Well, all these kind of things. So if you don't open up that FOX, what's gonna happen? Just curious. What's gonna happen? You dope that N plus material or P plus material into that wafer. What's gonna happen? It doesn't stay, or it won't be able to get through. So there will be probably a little diffusion here, but it's not functioning, right? You need all the N plus and P plus getting into the P substrate, so getting into the wafer, in order to form some functioning materials, okay, or transistors. So active layer of the mask, the active layer of the mask opens up the FOX layer on the top of the P sub. Any question on this? So let's look at the unselected P select. So you'll see this bigger box always happens with the active layers. So what you are going to see is something like this. Let's say this is N act, okay? N act, this is N type act. So eventually it's gonna dope N plus in here. And this is called the N select layer. Yeah, it just shows up at the same time. In electric VLSI libraries, you will see all these components have two different boxes, like one box here and one bigger box outside of it. So the bigger one is N select, the smaller one is N active. So the N active opens up the FOX, so definitely, because this is aligned with the FOX, with the opening over here, the area of the opening. But however, the N select is slightly bigger than this opening. So eventually the N active is actually not the window to allow the N material to get into the wafer, but the N select is. Why is that? What's the reason for that, you think? Because the fabrication process will not be perfect, and you think you exactly open up this window here and you want to directly deposit the N plus material into this window, there will be a misalignment. So eventually it won't be perfect. What's going to happen is you don't want to directly deposit through that inactive window, because the inactive window will be probably misaligned a little bit. Okay, or when you are applying another layer of mask, trying to deposit materials through it, you want to use a bigger opening here instead of just exactly the inactive opening. You want this to be bigger. So that's why we have an N-select, which is slightly bigger than it. So eventually when it runs through all these or deposit all the unplugged materials in through that window, even though there will be some hitting that fox on the edges, which is fine. You can guarantee that all of these areas getting diffused by this unplugged material. Okay, that's why the unselect layer is a little bit bigger than the inactive. So open up the window, and then use a bigger window to deposit the material, to let the material go through. These are all nano features, nanoscale features. So it's really tiny. There will be misalignment. So you use a bigger box to avoid all these or offset all these misalignment for the masks. Okay. Let's see what else I want to talk about. Okay, there will be another layer. Sometimes you'll see it's even bigger than unselect. It's even bigger than unselect. And it probably doesn't make sense to you for now, like why you need an even bigger one. So that one deposit N-Well here before you have a fox on it. Okay. But sometimes if you see a bigger box around that unselect, you just need to know that this is probably a while. Okay, N-Well. Let's move on to the polysilicon layer, poly. For the gates, okay, for the gates. For this part, I think first we need to know there's a gate oxide. If I draw it here, N plus, poly. It's a gate, should cover the entire field, the entire channel. And here's another layer called gate oxide.
Not really, we can't see.
Okay. Gate oxide. 2 more minutes, just finish all these polysilicon layers, will be done. Right. So that's the polysilicon layer to form the gate. So we'll talk about how the gate and the channel, how that works for the CMOS transistors on Wednesday. But there will be a gate material on the top, and in between the gate and the substrate, there will be a dielectric material. It's an oxide layer, which is called GOX, gate oxide. Okay, and sometimes this is another thing you guys need to know, starting from lab 3, I think, because a lot of times you are trying to connect the gate or have an extended length of the gate wire, but you need to know that you shouldn't use a long gate material, poly material, because it has a larger resistance compared to metals. So what you want to do is whenever you have to connect the gate to something with a longer distance, you want to drill a hole to the top, to the metal one first. Here's the oxide layer. Right, here's metal one. You want to connect the metal one first, and then use the metal one to route it, instead of directly using the poly wires to route it. It's a pink gate color. It's a pink polysilicon layer, and you don't want to use this one for longer distances. Okay, so there's one way you can use polysilicon for relatively longer distance, but the only way to do that is go through a certain process, and we are not going to do that, I think, for this class, because there's no fabrication for this class. So you have to specify that for the with the manufacturer. So you want to tell them you need a certain layer on the top of the poly. So let's draw it here like this. Okay, so just you need the manufacturer to deposit a certain layer on the top of the poly, and this is called silicide. So it's trying to kill that kind of resistance of the polysilicon, and it's usually made from tungsten. No, did I spell this right? Tungsten. I don't know, I couldn't spell it for now. Just the metal. So deposit the metal on the top of the polysilicon to reduce the resistance. Okay? Okay, so next time on Wednesday we'll cover the operation of CMOS transistors and a little bit more about the layers. Okay, see you later.